as was mentioned, I am a chemist over at the Air4L Space Vehicles Directorate, and I wanted to just talk a little bit about the work that I've been doing to try to develop solid oxide fuel cells for use on space vehicles. And so just, okay, next slide. I think there's a little bit of delay here before I see it. Okay, so the motivation for this is effectively spacecraft to be able to do anything. They need a lot of power. So just looking over on the right here, this is the energy bed of a CubeSat. And you can see that kind of all of the tanks technologies, all the things that you want it to be able to do, it's going to actually need to consume power. And so from that perspective, you say like, okay, well, I want to power all these things. So the natural thing is you would try to add more batteries into the system, you add more solar cells, but that can be really, really tricky because just getting into space, you're extremely volume and mass constrained because just lifting something up into orbit, that's a lot of mass. That's going to cost you a lot just in terms of getting a launch vehicle for that. And then even if you are able to get that mass up in space, you're also very volume constrained because the launch vehicle itself only has so much storage volume. So you can't just say, oh, okay, well, I got something really, really light, but you might not be able to fit inside the compartment that you need. Okay, next slide, please. All right, so try to mitigate this. What we've been thinking about at the Air Force Research Lab is like, okay, well, we have energy on board the spacecraft. Maybe we can find different ways to be able to use that. And so the inspiration is largely just talking about cars, is that with a car, you fill up the fuel, and then that automatically, not only does that give you something to power your internal combustion engine to give you that zoom zoom, but it also gives you all that electric power to get the radio to work and all the other fancy gadgets on there. And so from that perspective, we've been trying to develop this BEEPS, which is called the Bipropellant enabled electric power supply. And the idea there is that we have a spacecraft and it's going to naturally have this propellant that's on board. So because spacecraft needs to have thrusters to be able to orient themselves and be able to maintain their orbit, to do orbit keeping, to be able to complete different missions, to be able to dodge this or that if something comes flying at you. You can see some commercials about that from Space Force, like, oh, here comes debris, we got to maneuver out of the way. So now that we have this propellant that is on board the spacecraft, the idea is like, okay, can we actually pair that with a fuel cell? And so in that particular case, then if we have the fuel cell there, then we can use the bipropellant for thrust. Maybe we only need to do thrusting, and then that energy always can just be used to do maneuvering. But we have that fuel cell in place there. We can actually tap that chemical energy if we need to be able to power electrical systems. Okay, next slide, please. All right, so what does this actually gives us this benefit? What's the big advantage of doing that? Because it does introduce some complexity. And if you're familiar with spacecraft manufacturing, any type of complexity is definitely frowned upon, because the more complex something is, the more the ways there are to fail. Well, one thing is that fuel, that's kind of the best way we can store energy. I mean, if you just compare the amount of energy you can store inside a fuel cell power car for a given volume of mass compared to just batteries, I mean, the fuel cell just wins. You don't see people powering buildings with batteries. You can do the same thing with the diesel generator. So it's just by switching over to tapping the bipropellant to be able to store your energy, you can just store a lot more energy. So to show over here are some charts, just some rough estimations about just how much additional operational lifetime we can get from a spacecraft just by switching over to a fuel cell with regards to the mass costs and the volume costs. Another big thing is that with the fuel cell, we don't suffer from any self-discharge. There's no expiration date on when this fuel has to be able to be used. That can be great because if you ever track any of these space launches, you might be one of the situations where, okay, you put your everything's all packed up, it's all ready to go, but it might actually just sit on the launch pad for a couple of years and maybe a decade before it actually gets launched into orbit. And so the idea that once we actually power up this system and we don't have to suffer any type of self-discharge, we just know that that power is going to be available is really advantageous. And then there's also some idea about just in terms of designing spacecraft, right? So the fuel cell, if you're familiar with them, they have one reaction chamber. And so that gives you a specific power and specific power, voltage, and current output. And so as a consequence, that one thing can be designed specifically for one specific spacecraft. And then we say like, all right, well, we want the spacecraft to last a little bit longer or maybe a little bit shorter. And then all you have to do to be able to up or down that operational capacity is that you can expand the storage tanks for your bipropellant. So it's kind of the same as with a car that, okay, I can get more range if I double my gas tank. And then finally, when we talk about, one of the other reasons why we care about this, the solid oxide fuel cell is that a lot of people use a variety of different types of bipropellants. So depending on your spacecraft, folks want to be able to use different types of fuels and oxidizers. And so the idea about the fuel cell is like, okay, well, if we have this fuel cell here, whatever type of bipropellant we use, we'd be in a situation where we can actually convert it into electricity. And so that's where with the fuel cell, we've been looking into saying like, okay, can we actually make it so that it can be compatible with a whole variety of different types of bipropellants? And so my final point is with a fuel cell system, we can similarly enable refueling operations. And so with refueling operations, what we're talking about is actually getting a spacecraft to rendezvous with a gas tank, gas tanking station. That can be really, really tricky. So we want to try to say that when we actually get those actually to rendezvous, we want to simplify our operations by enabling it so that all we have to do is just refuel. So if we have this bipropellant consuming fuel cell system, all we have to do is, instead of saying like, okay, maybe we need to actually replace batteries, we need to tie things to just charge it up, it would be the exact same thing as with the car, where we can actually refuel the thruster while simultaneously refueling the energy stores for the electrical systems. Okay, next slide, please. Okay, so to actually realize this capability, there are a bunch of challenges that we need to overcome. The first part is the electrochemistry, where we have to start to think about the different types of electrodes that we're going to use, the electrolyte that we actually have. That's what actually makes up the fuel cell. We are also looking into just like, well, if we actually build a fuel cell, how do we make it work better? So that's what we're focusing on the operations to say, okay, well, how fast should we feed the fuel and the oxidizer? What is the operational temperature that we want to apply? Okay, we have the exhaust, do we want to recirculate anymore? Bipropellant compatibility, that's a big issue because as I mentioned before, people all want to use their own little types of bipropellant, like hydrazine and nitrogen tetroxide are pretty favored, but there's also interest in using different types of other types of bipropellant. So we want to have that bipropellant flexibility. Can we actually make something that produces useful voltages and currents? That's a big deal because people talk about power, but I generally don't like that because I think that obscures the complexity of the fact that sometimes you need a lot more voltage, your ability to push electrons, and then sometimes you need a lot more current where you need to have a whole bunch of electrons flowing. Temperature control. So if we're saying like, okay, if we have a solid oxide fuel cells, we need to be able to operate at temperatures over 600 degrees centigrade. That's a not trivial thing to do. I mean, it's hard to get over 600 degrees centigrade on the ground. So you can imagine the complexity just jumps up when you go up into space. Managing fuel and oxidizer flows can be really, really tricky because that is just saying like, okay, I have fuel and oxidizer. This is a flowing system. These things are going to be moving around. That's a lot more tricky than just being able to put in little battery cylinders. And then there's the whole idea about if we actually make the system, the fuel cell is able to provide a lot more power. So it kind of sets us in the situation where we have to reimagine what type of space operations we're going to actually perform. Because all of a sudden, if you have a lot more power, you can just do a lot more stuff. Okay, next slide. All right, and so this is where we're attacking it. So at first part, we're doing a basic research level. We're making actually these button cells. So you can see over on the upper right there, those are pictures of just commercially available fuel cell buttons. So all the key components are there, an anode, a cathode, electrolyte, and different current collectors to be able to actually extract and support that electron movement. The whole idea about this particular setup is that it's a very rough, simple setup where we have the fuel cell button and it's pinched by two different cylinders which bring in the fuel and the oxidizer. And the whole idea here is that we wanted to have a system where we can just rapidly be able to test the different types of fuels and oxidizers we put in and also the different types of button cells. Okay, next slide, please. And so with the solid oxide fuel cell that we're looking at, here's just some of the preliminary data that we've been able to get. This is all the voltage versus current density plots. The big thing to see is that what we've noticed is that when we take a look at the open circuit voltage, all of them, depending upon the mixture we use, like whether it's hydrogen fuel, ammonia fuel, nitrous oxide oxidizer, oxygen oxidizer, all of them all have an open circuit voltage that are about the same. And so that's what we're starting to say, that, okay, well, regardless of what type of fuel that we're putting into there, just because of the high operating temperatures of the solid oxide fuel cell, we are in a situation where we actually break it down into hydrogen and oxygen. And so that's fantastic, because it's like, okay, yeah, just by using this kind of solid oxide approach, we already introduced fuel flexibility, because effectively the high temperature brings everything back to a standard hydrogen and oxygen setup. Looking at the chart only on the left, results are showing that, yeah, oxygen and air and nitrous oxide, they're all viable oxidizers for the hydrogen gas. The linearity is showing us that the way that we've been interpreting is saying, okay, the biggest problems that we have are the electrolyte resistances, just the movement of the ions through that solid state material. That's kind of to be expected. You don't expect ions to be able to move through ceramics too particularly well. One thing that was a little bit surprising was the fact that looking at the slopes, it seems that the oxygen well, the oxygen system worked the best, but it seems like the air system actually outperformed the nitrous oxide. That was a little bit surprising, just because nitrous oxide has a lot more oxygen content per unit mass. And so we would actually thought that, okay, well, the people put these things into funny cars and so forth, that we would actually get better performance with the nitrous oxide, but that was just not the case. So one of the thoughts about that is just like, okay, well, the reason why this is happening is that we're just not completely decomposing the nitrous oxide. And then so looking at the other data, so if we move over to the middle chart over there, if we look at the ammonia is performing worse than hydrogen. This is not unexpected, just because we have an endothermic decomposition when we're talking about ammonia breakdown. And so the thought was like, okay, well, we have endothermic decomposition. That's going to lower the temperature of our fuel cell. That effectively lowers the ion mobility through the electrolyte. And so, yeah, we're going to have a kind of a power output loss just by putting in the ammonia. So the thing that was a little bit surprising is that when we start to introduce the nitrous oxide, that we also see this lower performance. And so with nitrous oxide, the reason why this was a little bit puzzling was because nitrous oxide, its decomposition is exothermic. And so we thought like, well, okay, if this thing's just going to just naturally generate some heat, this will be a big bonus. It'll allow us to have more heat into our solid state electrolyte. So as a consequence, we should have better mobility, we have better power output. But that was just not the case from the data that we saw. And so the hypothesis then goes back into reinforcing the idea that the nitrous oxide is just not fully decomposing. Okay, so next slide, please. And so that goes, now that we kind of had this idea of what the chemistry is actually doing, just by putting in these different types of fuels and oxidizers into our experimental setup, we're starting to attack. It's like, well, okay, this is the starting point here. How can we actually get things better? And so we're looking at a very basic science level where we say, all right, let's talk about the atomic level. This is what actually introduces the variety of chemistry that can be done. This is just saying like, okay, what type of elements do we put in? You have different elements, you can have different chemistry that's opened. We're looking at things in terms of the microscale. This is where we're starting to look at the reaction chemistry, like how do we get the fuel and the oxidizer interact with each other, what type of electrochemical actions can occur. And then we start to think about the meso level, where we're thinking about, okay, well, let's say if we can actually change the thicknesses of the different components, so we can effectively change the ion flux, change the mass flow, effectively change just the kind of these big properties, these bulk properties of the solid oxide fuel cell, just by tailoring things at that scale. And then finally, we're also considering the macro scale. It's like, okay, we got this very interesting device, maybe we can get it working as a button. Can we actually just package that into something that will be able to provide useful power over to power a vehicle of some sort? Okay, next slide. And so to actually be able to do these controls, the one big approach that we've been taking is additive manufacturing. And so additive manufacturing is awesome because you're in a situation where you're actually being able to put down specific chemicals, put down specific elements in very precise ways. And so the idea here is that to attack that atomic level, we were always thinking about, okay, well, what type of inks can we actually prepare? That's the ink formulation. So saying, all right, now that we know that maybe chemical X, Y, and Z are great, maybe we can make an ink out of it. And so by preparing an ink, we can then now enable this additive manufacturing to be able to lay down those things to either become an electrolyte or an electrode on the solid oxide fuel cell. The next big thing is that with the additive manufacturing, is you can start to actually layer things. And so that's starting to give us that, that meso control, that micro control, to where we can actually be able to control the electrochemistry. The thermal processing is coming in at the end, so we actually be able to say like, okay, now we actually laid everything out. Depending upon how we treat it, we can actually form different types of bonds, form different types of structures, have different types of porosity within our system to be able to have particularly strong performing solid oxide fuel cells. Okay, next slide, please. Okay, and then here's some images about our additive manufacturing of solid oxide fuel cells over here. This is a YSC supported, anode supported fuel cell, and you can see that, okay, yeah, we're able to lay down what we wanted to, we get the chemicals where we want. You can see that actually the fuel cell part there is a very, very small layer over there. So this is saying that additive manufacturing is a targeted way where we can actually make specific fuel cells of a particular design. Okay, next slide, please. And then just to say like, okay, we know we can start to realize this manufacturing of these particular fuel cell buttons so that we can do the experimental work to try to really understand the chemistry. Instead of, while we're definitely doing some combinatorial work just to say, okay, well, we've read about this in the papers here and read about that in the papers there, so that we can say, well, let's just try them out. But we're also applying a whole bunch of different computer simulations, in particularly this Matlab and Simulink type system to be able to just model the entire system. In that way that we can start to be able to guide our additive manufacturing to be able to say like, okay, well, what type of porosity should we have? What type of chemical gradings should we have? What type of chemicals should we actually introduce into our system? Okay, next slide, please. And then also we use these simulations to be able to calculate performance. And so as mentioned before, temperature is a big deal for our solid oxide fuel cells. And so showing over here is a simulation actually just to be able to predict the temperature gradient of the solid oxide fuel cell over just on the electrode side, where the fuel is effectively introduced onto one side and allowed to flow over the electrode to pass through it. And so, yeah, as you can see here on the charts, over on the left, when the ammonia is flowed over the electrode, right away, we have a very big temperature drop that's consistent with our endothermic decomposition. And then as that decomposition occurs, and then you can see with this dashed line, it starts to raise up until finally when it's over at the 20 centimeter mark, it's the temperature's high, because effectively this is consistent with our thoughts that once the ammonia breaks down, it just makes hydrogen. Now we have an exothermic reaction. And then just showing how you have those little domes there, that's where we try to introduce co-flow. We're saying, okay, we have ammonia coming on one side, ammonia coming on the opposite side together, so they actually are going in opposite directions. And you can see that we get this cooling effect over onto the sides. And so that's kind of the way that we're applying these simulations to say, okay, well, fundamentally, what type of chemistry is going on? What type of dynamics are coming on? What type of temperatures are we going to have? And that allows us to actually start to consider what type of design we want to have. Because it makes sense, if we set up this particular set, we can say, okay, yeah, now that the sides might be a little bit colder. And so that introduces maybe different ways that we can actually seal and package the device. Okay, next slide. Another thing we're looking into is we're talking about this bipropellant compatibility. Bipropellant is going to explode. That's the whole point. It's going to make a lot of heat and energy and send out a bunch of gases. That's how you get your thrust. And so there's the idea that, okay, well, people generally want to put, when we look at the fuel cell research, they're generally putting in hydrogen and oxygen. So that doesn't going to spontaneously explode. You do need a spark. But with the bipropellants, we are talking about hypergolic. So as soon as they mix, they're going to have a big explosion. And so the other idea is that with these bipropellants, because they're very energetic, if they are energetic, that means they're going to be very reactive. And so they're very reactive, that means that they're going to just be able to, there's a good chance they're going to be able to chew through everything. And so that's one of our big concerns right now. It's like, well, how do we actually create fuel cell components so that one, they're able to be tolerant of the bipropellants, which can be corrosive and damaging. And then two, that they don't actually just break through and actually can interact with each other and cause an ignition and just blow up my entire spacecraft. Okay, next slide. And then this is also, once we actually have this all going together, there's the idea of saying like, okay, well, what can we do to kind of track and treat maybe the bipropellant? How can we actually facilitate the actual decomposition of particular bipropellants into gases that we want, in particular maybe this hydrogen. And so that's where we start to have a whole bunch of experimental capabilities where we're actually looking to say, okay, well, how can we actually look at our exhaust gases and then be able to track what type of chemistry happened inside our chamber. And so shown over here is just looking at how do we control the decomposition of hydrazine, and saying, okay, well, if we start to tinker around with the temperature and the pressure, that's going to affect the chemistry, and then we can track basically which one of these decomposition pathways are listed here, the 1 and 2, based on just the population of the hydrogen gas that's produced. Okay, next slide. And then, of course, to be able to do all that tracking, we have a whole bunch of experimental equipment that's set up. This over here is the FDI mock-up of the FTIR system, where we're looking at over the exhaust gases that come out after our fuel cell is in operation. Okay, next slide. And of course, this goes back to finally the packaging. So I heard MOXIE was mentioned before. MOXIE is great. It's an electrolysis cell that's breaking the carbon dioxide on Mars into very ultra pure oxygen. So one of the people that we're working with, they're the ones that actually built this MOXIE stack. And so the reason why we are working with them is because they actually get that solid oxide fuel cell system up to Mars. So that means that it survived both the launch, that very long travel through the radiation environment to get to Mars. And then they also survived landing on Mars. So these are very robust, aggressive conditions, which just chop down most solid oxide fuel cells. If you've ever actually worked in them, I play with the button cells myself, and they're very, very fragile. So it's the fact that a MOXIE system has able to survive this deployment onto Mars. It means that it proves that a lot of the stuff about making something robust to be able to tolerate the kind of the abuse that a vehicle would experience can be solved. Okay, next slide. And then this is a little bit more details about just kind of the stack that they have onto the MOXIE system. Next slide. And then just the overall housing, the way it's all set up. This is one where we took the MOXIE equipment, the design stack, and then actually just made into a solid oxide fuel cell. So this is a mock-up of kind of our adaptation of MOXIE into a solid oxide fuel cell. In this particular case, being able to, works reversibly, that's over in our lab right now. Okay, next slide. And so just kind of a quick summary of the things that we've figured out so far is that it is possible to actually run fuel cells with bipropellant, and that bipropellant decomposition seems to be a big deal. But we do recognize that there's a significant amount of work to actually be done to actually make the fuel cells to be something that can be integrated into a bipropellant thruster and be able to be sent off into space. And so the things that we're looking for, and so these are talking to all the researchers that are here at this conference right now, are certainly more new fuel cell components, electrodes, electrolytes. We're thinking about different types of seals. Okay, we got to make sure everything actually stays where it's supposed to be and things don't mix in appropriately. And we're trying to think about, okay, what type of new fuel cell design should we be considering? Okay, next slide. And this is an overview of the team that is available to, or that to talk to folks if you like to reach out with us. I'm listed over there on the main point of contact. And then we have many collaborators over at the different Air Force directorates, Materials and Manufacturing, Aerospace Directorate over at Ohio and California. And then of course, Oxion, which has made the MOXIE stack. And then you can see over here, it's color coded based on the expertise that's being brought to the table to try to realize this fuel cell system. Next slide. I believe that's it. Okay, and then so we're moving on to the Q&A section.